All right, everybody. It looks like we're online. There do seem to be some technical issues this morning. I think they're actually on YouTube's end, which is, I was getting a message from YouTube that says streaming wasn't available. So hopefully we can get through this together. Today, our goal is to finish talking about linked lists, and we'll also take some questions about the midterm, which is on Wednesday. This is the midterm on object-oriented programming. But first, we're going to go back and review a little bit of the material from Friday about linked lists. Hopefully you guys had a chance to work on that homework problem over the weekend. There is a homework, I want to clarify one thing, I'll get to this towards the end of today's class, but there is a homework on today. That homework problem is not due until Wednesday. All right, that gives you a little extra time to prepare for the midterm exam. Starting Thursday, we'll be back to our normal rhythm of doing daily homework, and pretty much in that rhythm throughout the rest of the semester. All right, so the idea behind the last sort of set, this era of homework problems in the class right now, is that you're building something called a list. A list is a very general purpose data structure. It's a generalization of an array. It's an ordered data structure, so it puts the data inside it into order. It brings a piece of metadata, each data item, which is its position in the list, right? And that positions it relative to the other data items that are also part of the list. Like an array, a list allows us to get and set values by indices. So we can change a value in a list and we can retrieve a value from a list using the index if the value is already there. But unlike Java arrays, which are fixed size, lists support operations that modify the size of the list. So that includes inserting an item at any point in the list and removing an item at any point in the list. Depending on where you put the items, certain lists have special names for those operations. Sometimes at the beginning of the list, we call that shift or unshift. At the back of the list, we call that pop or push. It really sort of doesn't matter, right? The idea is that with the list, unlike an array, I can insert an item in any position within the list. That modifies the length of the list. That creates a longer list. And in contrast, I can also remove an item from any place in the list, and that modifies the list by creating a shorter list. And lists are a very useful data structure. Normally you're going to use the built-in Java lists or Python lists or Go lists or Haskell lists or whatever to do these type of operations. But by implementing it, you're getting to see a little bit of what's going on behind the scenes. And this is also a great chance for us to be able to compare and contrast two different approaches to providing the same interface. Because the array list that you finished building last week has very different performance characteristics than the linked list that you're working on now. And they're good for different things, right? So this is one of these fun trade-offs that we get to talk about at this point in the class, right? Is the trade-off between different ways of doing the same thing. So again, this is a nice sort of convergence of a lot of the ideas we've talked about. We're using inner classes on our linked lists. We're using encapsulation in both cases. We're using interfaces. Both of these lists that you're producing conform to the same interface. So from the perspective of somebody using those two lists, they behave identically. They both support the same operations with the same semantics. So I can take your code, and if you have cast your simple array list to a simple list, and you're using it as a simple list, I can replace the place where you created as a simple array list with a simple linked list, and the rest of your code just works perfectly. And the idea is your code doesn't have to care how those operations are being implemented. And because you're building them, you're actually getting a first-hand view into exactly how the implementation works. And this is also going to allow us to point out some interesting some interesting trade-offs between these two data structures, right? In terms of how they perform the same operations and what performance results from the different design choices that are happening internally, right? So lists are going to be our first example of this, but we will come back and talk about this, particularly when we get to the part of the class where we talk about sorting algorithms, because sorting algorithms are a great place to discuss this. They all perform differently. They have different trade-offs in terms of best case and worst case performance and things like that. But for now, the idea is that if you think about a high-level view of these trade-offs, and we've seen the code behind this, right? So we looked at the code for get and set for an array list, and it was pretty clear that this was O1. All it was doing was an array lookup, right? But when we needed to modify the list, now I've actually got to create a whole nother array, copy everything over, and so this is a much slower operation. In fact, it's an ON operation. In contrast, the linked lists that you guys are working on right now have very slow lookups because anytime I need to find anything in the list, The only thing that I know is where the list starts. I don't know how many items are in it, and I certainly don't have a way of accessing an item in the list through a single operation like I did with an array list. Instead, anytime I want to access one of the items in the list, I actually have to start at the beginning. Take that start reference and start walking that list all the way until I get to the item in the position that I'm looking for, or sometimes until I get to the end of the list and I realize that somebody asked for an item that's off the end of my list, right? So you might think, why is this good, right? What's good about this list? It seems like anytime I want to do anything to it, I need to look up an item. You guys, we saw that helper function that's basically like find a particular spot in the list. But it turns out that some operations on linked lists are extremely fast. So particularly operations that operate on the front of the list. And it turns out we can also make operations that operate on the rear of the list, the end of the list, fast as well. We'll talk about how to do that later. All right. Both these implementations also provide different memory usage trade-offs, and that's something, again, that we'll come back to and talk about when we get to the point where we can compare. So this is the interface for the list that we've been implementing. This is a simplified version of the Java list interface that only contains the methods that really do the work. But this is really all it takes to be a list. I have to be able to look things up by index. This is an ordered data structure. I'm putting items in order. And I need to be able to add and remove items, right? So I need to be able to put things into the list at various points, right? So another way of doing this, so we looked at array lists. You guys have already built those, right? And the way that we started talking about on Friday, and you guys started working on over the weekend and are continuing today, is this idea of using something called a linked list. So the key question to think about when you implement a list is how do you maintain the order, right? The way that an array list maintains the order is that it put everything into an array. An array is an ordered data structure. So an array list is really just sort of wrapping an array internally, and it's utilizing the fact that Java already provides you with an ordered data structure. Now again, that array data structure has problems. It doesn't allow you to modify it in ways that would change its size. And so the array list class, your simple array list class, is basically wrapping an array and doing some more work behind the scenes to remove that limitation, right? In add and remove, you're actually doing copies between two different arrays of different sizes so that you can perform operations so that the person using your list can perform operations that would modify the size. However, there's another way to do this, and the other way is through something called a linked list. And linked lists are really fun to talk about. So the idea of using linkage to link items together into this type of data structure actually gets used all over the place, right? You might think that this is sort of a weird digression into something that doesn't seem as foundational as an array list. When you program in Java, I'd say 95% of the time you're going to use an array list when you need a list. But it turns out in a lot of systems and a lot of other applications, linked lists get heavily used. And so this is a good chance to introduce you to some concepts behind linked lists that you'll then see again, potentially when you get on to 126 or to 225 or 241. I know you definitely will, right? A chance to practice with them in Java where things are a little safer and easier. And then hopefully when you get into some of those later classes that you're programming in lower level, gnarlier languages like C, this won't be so intimidating. Okay, so the idea here is a linked list establishes order by simply making sure that each item in the list knows what the next item is. And that turns out to be sufficient, right? So again, think about this analogy of creating a list within the students in this class. So if I sent you all an email and all the email said was the next student in the list is X, and I gave you their email address, right? Then I could actually send an email chain that would reach all the students as long as you guys all followed my instructions. So I could link the entire class together in such a way that all I had to do to email the entire class was email the first student. And then that first student would send an email to the next student would send an email to the next student, et cetera, until it got to the entire list. It turns out that actually in the past, I don't know if people still do this, but people used to actually set this up. This was, I can't remember exactly what the name was, but it was like a phone chain or something like that. So for example, let's say that your family trip was canceled and you need to let everybody know really quickly. You would set up a system so that one person will call a few other people and stuff like that, right? And those people will call more people, and so that way you can get the word out quickly to a lot of people. But anyway, in this way of establishing a list by linkage, right? Again, all you need to know is the next person in the list, and you don't even know how long the list is. there's only one item in the list that knows something special about itself, and that's the last item, because the last item doesn't have a next reference or a next person in my example, right? So here's our item class. So this is the internal class that we're going to use to structure our linked list. That item class contains a value. That's the data item that we're actually storing in the list. It also contains a next reference. So again, each item in the list knows really two things. First of all, what value is stored at that position in the list. And the next thing is, what's the next element in the list, okay? And then there's a little simple constructor to create that. So the question is, how do I create a list using this simple building block? And it turns out, again, here's a way to do it, right? So in this case, this item's reference is my list, okay? So this is the kind of like the start that you guys would be using. And what I'm doing here through a series of calls is I'm actually adding items to the front of the list. So you see that as I create new items, I started with an item with value 0, which ended up at the end, and then I added 8 and 5. And here's what I do each time. So let's look at what happens when I add the last item. So here's what the list looks like before I add this item. The first item in the list is an item with value 8, and the last item in the list, or the second item, is an item with value 0. So I'm about to add a new item. What do? I create a new item with value 5, right? And I set its next reference to the former start of the list. So this item 5 has a next reference which refers to item 8, which was what items referred to before this call completes. Then I reassign the start of my list to refer to this new item that I just added. So now when I'm done with this particular step, I have a list that looks as follows. Items is the front, and then I have item 5, item 8, and item 0 linked off of that list. So you guys have been working with this simple linked list class, and you've been starting to flesh out the parts of it that you need to complete in order for it to conform to or to provide or implement the simple list interface. And so once you're done, this linked list is going to behave exactly like the array list that you have already implemented. So let's look at, and this actually, I think this was the weekend homework problem, or maybe it was in today's homework problem. But let's just look at a special case, right, of add, okay? It turns out with linked lists, it's kind of interesting. Get and set turn out to be hard because they actually have to move to the right spot on the list. We'll talk about how to do that in a few slides. But let's look at a special case for our linked list, which is how do we add an item to the front? And it turns out that this function is really simple. This is add to front. It's a special case of add. It doesn't handle every case of add because it only handles the case where I'm putting the item in the front of the list. But look at how simple this is. I have all my simple linked list maintains is a reference to the first item. That's all it knows about the list, is where is the first item. Then when I want to add an item at the beginning, I pass in a value to my add to front call. I create a new item with that value, and then I set its next reference. So the question it needs to know is, where's the rest of the list? Well, it's at the front now. So the rest of the list is whatever was, whatever start referred to before I started this call. So start might be null, in which case this is the only item in the list. Start might refer to a list that has 10 elements, in which case this is the first item of a list that now has 11 elements. It doesn't matter. All I do is I set the next reference of my new item to refer to the rest of the list, and then I set the start to refer to this new item, okay? Now if we look at this, remember add and remove from our array list. They always had to copy all of this stuff around to create a new array. So add for an array list had to create a new array with room for this new element that I was about to add, right? That room needs to be made somewhere, and so I have to copy the array, I have to copy everything over, and now I have an empty slot at the beginning that I fill with the new item. So it's an ON operation. Here, what's n? Well, if n is the size of the list, which it typically is for our list operations, the performance of add to front is O1. It never takes more than one step. The only amount of time I have to spend is the time it takes to create this new item. Okay? Now again, this is a special case of add. In the general case of add, once you finish that, you're going to find that it takes ON because I have to find the place to put the item. But it turns out that this is a case where add to front, so the special case of add. Remember, a lot of times when we talk about performance, we're going to think not only about the worst case, but also about the best case. And the best case performance for linked list add is 01, because it's right at the beginning of the list. And it turns out that the beginning of a list and the end of a list are frequently places where certain algorithms are going to make modifications. There are some algorithms that only add or remove items from the front or the end of a list. And so if we can make those operations fast in this way by using a linked list, then we can better support those particular algorithms that need that capability to be fast. Now again, what's the catch here? So, we did something quickly. We have a new feature. So with an array list, add was always ON. It didn't matter where the item was. With a linked list, add can be O1 if the item is at the front. And it turns out it can also be O1 if the item is at the end. We'll talk about how to do that later. But what's the catch here, right? The catch is that get and set, which were easy with array lists. So remember, with an array list, it's like 2 lines of code, right? I checked if 3. I checked if the index was okay, and then once I knew the index was okay, I just tried to grab the thing right out of my array. It was done. With a linked list, we're going to have to do more work in get, because remember, the linked list doesn't know where any of the items in the list are. It only knows where the first item is. So again, if I linked all the students in the class together using this system that I was proposing before, and I needed to find student number 50, I would have to start with the first student, ask them who their next student was, and ask them who their next student was, and I have to repeat this 50 times. Okay? I have to do that every time I want to access a certain element in the list. So I have to start at the front, and this is referred to as walking the list. I need to start at the front, I need to figure out where the first item is, I need to use the first item to figure out where the second item is. I use the second item to figure out where the third item is. And I repeat this process until I get to the item that I want. So, let's look at an example of this. Let's say I have a list that has 3 elements, right? And let's say that I want to get the second element. So remember, the linked list itself only knows where the start is. All that is saved in my simple linked list structure is the start. I don't have a reference to item 1. I don't have a reference to item 2. All I have is my start, which at this point in the list construction refers to item 3. So how do I get to the third item in the list, the item that's at index 2? Well, I have to start at the start. That gets me to the first item, and I'm sort of counting as I go. So this is item 0, right? We start at 0. Then I follow its next reference to get to item 1 with index 1 with value 2. And then I follow its next reference, and I get to the item with index 2, the third item in the list that happens to, in this case, have value 1. I just put the indices backwards from the values just to confuse you. So again, let's look at how this works. We start with the start reference. We use it to get to the first item in the list. We use it to get to the next item in the list, and it to get to the next item in the list. And I repeat this process until I reach the index that I want, right? So again, let's start to think about how we would do this and what the performance of this particular operation would be, okay? And it turns out that you can iterate through a list using a loop. And that loop you guys have already been practicing with last time. That loop looks a little bit different than the loops that we've used in the past. So let's work through it together, right? Okay, so let's look at a little piece of code together. This is our simple linked list class. It has the only instance variable I have here is a reference variable named start that's of type item. So this refers to the first item in the list. I have an inner class here that's going to describe the items that this list stores. This is an inner class because nobody else should be using this class. This class is not visible to the outside. So none of the methods in my simple list interface that I'm eventually going to complete implementing return an item. They return objects. So the way the simple linked list works is it uses its linkage to find the right item, and then it's going to use the item to find the value that was stored in that position. All right, so I have a constructor here that I've created to allow us to just get started here. And the constructor is sort of interesting, right? So I've implemented add to front. That's a very simple case of the implementation where all I'm doing is I'm adding an item at the beginning. And then because add to front is so easy, I use it in my constructor. And the idea is I want to be able to take an array and convert it into a list. To do that, I go through the array backwards. So this for loop that's right here actually goes through the array in inverse order. It starts at the last index and it works its way back to the beginning. Each time it calls add to front and it passes the value that's in the array at that point. So when I'm done, I've added things to the front in reverse order, and so I have a list that has the items in the array that was passed to the constructor in the correct order. All right, so now let's go through and actually let's try to print all the values in our array. And the way we're going to do this is we're going to use this new for loop, right? The for loops we've been using so far have been for loops that increment an integer index, and those are incredibly useful for going through arrays. However, probably one of the most other common, maybe the second most common for loop you'll write in your life is a for loop that goes through a linked list. And this is a little different, but it uses kind of some of the same concepts, right? So the first question is, where should I start? Actually, the first question is, what is my loop variable going to be? When I walk through an array, I want my loop variable to be something that I can use to index the array. Here, my loop variable is actually going to be a reference to the item that I'm currently looking at. So I'm going to call that current, and I'm going to initialize it to be the start of my list. So the first item I look at is whatever is referred to by start. Now let's actually go and do the last part of it first. So how do I increment this loop variable? Well, I don't increment it, but how do I update it? I want to update it by getting the next item in the list. So what I do is I say current is equal to current.next. That will get me from the current item to the next item, right? Because each item has a next reference. Okay. Now, when do I stop? Right. So this is an incredibly important thing to think about. I continue as long as current is not null. All right. When current is null, what this means is that I've gotten to the last item in the list. I got to the last item. The last item in the list has a next reference of null. So I set current is equal to current.next. Current ended up as null, and that means I'm done. I visited all the items in the list. And now, for now, let's just put some code in here that just prints the value at that point, and see if our code will do something useful. And it seems to, right? And here, I'll just put something in here, just so we know that it's actually our code running. It seems to work, right? And so, again, this is one of those for loops that's incredibly important and a very, very sort of canonical form of a for loop, right? It's quite different than the for loop that we use to index an array. Instead of I starting at 0, I start a reference variable at the start of the list. Instead of incrementing I go to the next item by setting my reference equal to the current item's next reference. And instead of stopping when I get to the end of the array based on its length, I stop when I've reached the end of the list. Now, one question is, will this work if I'm starting with an empty list? Let's say start is null. And the answer is yes, because remember, the condition is checked before I enter the loop body. So if start is null, if the list is empty, and actually let's just go ahead and do an example of this. I just want to make sure it won't crash, and it won't, right? If start is null, then what happens is current starts out as null, but I check the condition before I enter the loop. So current starts out as null, current, this is my condition that has to be true for me to continue, but in this case, current starts out as null, and so I never enter the loop, right? And I can put a printf here, just so we're all convinced that this actually ran and it's not just a trick or something like that. So, okay. So this is, and again, this is a loop that you've already seen in some of our example code for the homework problems, but this is sort of the canonical for loop that you use for iterating through a linked list. Okay, I'm going to jump over on the forum just really quickly to make sure that I'm keeping an eye on any questions people might be having. What's the difference between the purposes of objects and items linked? Okay, good question, right? So the idea behind our list is that I can use it to store any object, all right? So I can put strings into my list. Let's try that, right? Let's create let's pass in a list of strings, right? and nope, Jeff, let's go in here, right? So rather than integers, now I pass in strings. So my list can store any object, but that object goes inside each item. So every item in my list, this is an object that I've created that holds two things. It holds a reference to any object. That's the data that's actually stored in the list. And then it holds a next reference, and that's how I link these items together. So the next reference means that when I get to a particular item, I can find the next item in the list. Actually, let's go ahead and have some fun with this. So let's basically say, here we'll say if current dot next dot value, not next is not equal to null, then we'll say next, and then, so this is, we're going to use this to basically peek ahead one item in the list, right? And now I'll just make this a print. I'll put this guy here, and then I'll do a print, and then I'll stick a new line in here. Yeah, so now what you're seeing is, you know, each item in the list knows not only where it is, but it also knows where the next item is. So first time through the list, I'm at the item in the first position. Remember, this is an ordered data structure. The value there is here, but the next value, which I get to by using current.next.value, is there. When I get to there, now I'm at the second item in the list, item with index 1. The current value is there, but the next value is third. When I get to third, I'll put in an extra printf here, just to say that the next is the end of the list. All right, cool. Yeah, so in each item, right, I know two things. I know the value that was stored there. I have to know that because I'm storing data in this data structure. But I also need to know how to get to the next item in the list if there is one, right? And the idea is if my next reference is not null, I use that to get to the next item. And in my loop, I'm utilizing that capability, right? Great question. Looks like there's another question here. Let me go back to the... If simple linked list is extended to add another child class, is item accessible? How is the next value found? So I guess the question would be, if you extended this, would you still have access to item? So if you extended this, right now you would have to change this a little bit because start is private, so you can't even find the start of the list, right? But if you extended this, it's a good question. I don't know if the extension would have access to the item classes or not, right? We could try that, but that's a question that I'll probably answer offline. It's a great question. All right, so let's go on. So now we've looked at how we add to a list, but how do we actually insert? And this is the tough one. This is the one you guys are going to struggle with, right? But it's such good fun, right? Like, this is super awesome. It's one of these things that you'll have to do in the future. Like, it's just some fiddling around with references, and it's a little tricky to get right, but you will get it right, and you'll enjoy it once you get it right. And it's not the last time you'll do this either, right? So here's the trick, all right? And this is subtle, right? So we're going to go through it a couple of times. I'm going to walk through the algorithm first, then we're going to look at a diagram. Eventually, you guys, actually, I think starting today, you're going to do add for the next couple of days, and then on Thursday, you'll get a chance to do, Wednesday, you'll get a chance to do remove. So this is coming, right? You guys are going to get a chance to do this for real. Here's the algorithm. The first thing I need to do is I need to find the right spot to put the item. So let's say I want to have a list with 8 items, and I want to insert at position 4. Right, so this new item, when I'm done, is supposed to have index 4, and the list will now have 9 elements. So the first thing I need to do is to find the right spot. Then what I'm going to do is I'm going to take the previous item, I'm going to change its next reference to refer to the item that I'm inserting. I'm going to set the next reference on the item I'm inserting to point to the item that used to be the next item from the previous item. And then I'm done, right? And I'm sure that made a huge amount of sense when I talked it through in English. So let's look at a diagram here, right? So I want to insert value 7 at index 1. So again, I've got an item listed as 3 items. When I'm done, it's going to have 4 items. When I'm done, currently item 5 has index 0, item 8 has index 1, item 1 has index 2. When I'm done, item 5 is going to have index 0, item 7 is going to have index 1, item 8 is going to have index 2, and item 1 is going to have index 3. So how do we accomplish this, right? So here's the thing that's tricky about this. If I walk to the item with index 1, I've gone too far. If I get to the item with index 1, I can't do anything because the thing I need to change is over here. I need to change the next reference of item 5. Okay? So it turns out that the right spot in the list to walk to if I want to insert is not the index that I'm inserting, it's the prior index. And this is why when I add to the front of the list, I don't have to walk the list at all because the front of the list is index 0. The item before that is start. So all I do is I change the start reference and that works. So in this case, what I want to do is I want to walk to item 5. Okay? So I use the helper function you guys have already been working on to get to item 5. And then I do the following set of things. So here's my new item. First, I set item 5 to refer to item 7. So you'll see what's happening here. Item 5's next reference used to refer to item 8. Now I'm going to have it refer to item 7. Okay? So now I've inserted item 7 at position 1 in the list, but the problem is that I've lost the rest of the list. So now my list, the list that was after item 5 is detached. I need to reattach it before I can finish. To do that, I need to take the new item that I'm inserting, and I need to set its next reference to item 8. Now how do I know how to set its next reference? Well, its next reference is what item 5's next reference used to be before I changed it. Right? So this is one of those places where you have to be careful about how you swap things around because when you're doing this, you have to make sure that you maintain a reference to item 8. If you lose that reference, so let's say that you set item 5's next reference to item 7, well now I don't have a reference to item 8 unless I've saved it somewhere, right? So I need to save the reference to item 8, change item 5's next reference to refer to item 7, and then change item 7's next reference to refer to item 8, and then I'm done, right? So again, you guys will have a chance to practice this. I think we'll go through this again on Wednesday. This is not particularly easy stuff. It is super useful in terms of, one of the reasons that we work with linked lists in this way is to get you comfortable with working with references. References are really just a step away from pointers, which you will have to tangle with once you get to 225 and 241 and onto other languages. References are a safer version of pointers where there's fewer opportunities to shoot yourself in the foot. And so so this is a good chance to practice with this type of thing. If you can insert into a linked list in Java, you have a prayer of being able to do it when you get to 241 and have to do it in C. All right, so I will go back and I'll allow you guys to add questions to the topic. I'll go back and handle them in a second, but let me start talking about the midterm while we're doing it. Okay, so the midterm exam is going to be on Wednesday. It's going to be during class for most of you. If you are taking the exam at 6 p.m., I will email you on Wednesday morning and tell you that, okay? It is critical that you show up to the right exam, okay? There's only a handful of you that are taking the 6 p.m. exam. Those applications are closed. So if you're in that group, know you're in that group. You will not have access to the exam at 10 a.m. If you are in the 10 a.m. group, plan on taking the exam at 10 a.m. That's what we're going to do. I have talked to the people that run Prairie Learn. They have promised that they'll have more capacity online this week. So hopefully some of you that dealt with some slowness and other issues last week's quiz, those will be alleviated. Obviously, if something goes terribly wrong, we'll do something else, right? We'll handle it. But this is our plan. Okay, so the midterm is very similar in structure to the midterm you've already taken. There will be 10 multiple choice questions. These are entirely drawn from previous quizzes. They're not the easy 2-pointers, what keyword do you use to create a Java class or something like that. These are a little more substantive. They'll ask you to look at chunks of code and tell us things about them. There are 3 20-point programming questions on the exam. All have partial credit, right? So there are ways to get some points on each one of these problems. These problems should not be unfamiliar to you. As always, the best way to prepare for the midterm exam is to practice the homework problems. All of the homework problems you need to practice have been released. I released quiz 7, which you guys took last week. That's also available now on the Homework 125 problem set. So everything you need is there, right? The topic coverage is essentially everything up through last week's quiz. I put the dates of the actual classes that this corresponds to. So it's basically kind of a month from mid February when we started to talk about objects into the last class that we did on interfaces. There was no coverage of anything that we've been talking about since spring break. There's no algorithms, there's no algorithm runtime or lists. That stuff is coming. I'll be on next week's quiz. This is all on object-oriented programming from the basics up through interfaces, which we finished with. All right, so I will take questions on the midterm as well right now. I want to talk about just a couple of things before I do that. First of all, you guys are doing fantastic, right? I mean, people did a great job wrapping up MP3. I know these are difficult circumstances, and every one of you is dealing with a different set of challenges right now, right? When you guys are here on campus, things, everyone still deals with different challenges, but things are a little bit more normalized, right? I mean, for example, we assume you all have good Wi-Fi, right? We assume, some other things. You're not, having to deal with the stress of somebody losing a job or, right, spending time around people that you're not used to spending time around, maybe in closer quarters than you're used to spending time with people. So again, I mean, your circumstances are so individual to you right now. And that means that if you need help or if you need something from us, please ask. We really can't, this has made it more difficult for us to kind of predict who's struggling because, some of you that were doing really well when you were here may have a lot to worry about now at home or wherever you happen to be. So, if you need help, if you need extensions, if you feel like you're falling behind on something, please come and talk to us. We're happy to help. We want to do our best to provide the kind of support that you guys need to finish out the semester, if that's possible too, right? And I think there's some of you for who, it may legitimately be the kind of situation where you might feel like maybe the right thing to do is to come back and try again in the fall. And that's totally okay. And I think, if you're thinking about that, I would also encourage you to kind of, it's probably better to make that decision sooner rather than later. Because if you've got other stuff that you need to handle in your life right now and school isn't a high priority, I get that. But, stop handling the school stuff, right? Just drop that, let it go, and get on to the handling your life things, right? Because the sooner you do that, the less time you're going to spend if you end up having to come back in the fall, right? Look, this is a huge disruption to everybody's life. Things aren't going to go back to normal in the fall. In the fall, we're going to be dealing with this semester, and there's going to be, a long-term effect of this particular challenge that we're going through that's going to be felt throughout our department and throughout a lot of other institutions and across the world for years. And so, don't worry about somehow I've got to, just grit my teeth and get through it any way I can this semester, and then next semester I'll be okay, because if you don't understand the material, then you're going to struggle downstream. We want to make sure that everybody goes off and does great things after they get out of here. All right. So, as always, I know that a midterm exam is introducing a little bit of stress into your life. I get that. My goal is to get you to do the homework, period. So you do the review. No matter what happens on Wednesday, you have internalized, you're learning the material. The way that you learn this stuff is by practicing it. You don't learn it by taking a midterm. The only reason we get to have you take the midterms is that it causes you to practice, right? To get the practice you need to learn this stuff. All right, so let me also talk about how to get help. So, the first week back, I think a lot of us were just scrambling to get things, settled down a little bit. And now I kind of want to be more intentional about how we go forward with things. And so we have a variety of different ways for you guys to get help. The first one is the forum. As always, that's a great way to get help. There are CAs that have been staffing it and doing a really great job of answering questions, and we're going to try to continue to do that for the rest of the semester. We understand that, given a lot of you guys are virtual, this is going to be more important. Okay, we're going to continue to develop and maintain our new CS125 help site. If you haven't tried that already, give it a shot. I know some people are having issues with it. I'm working to fix those. Please be patient with us. This is brand new. I've had some really great encounters with people on that site, and we're going to continue to try to make it work, right? I have some fixes we're going to put in today, and that's something that we're expending daily energy on. If that doesn't work, so that's really the top, way of we want you to try that. We're going to continue to work on it, try to make it better. If that doesn't work, we are running a video chat, kind of a long-term Zoom video chat that you guys can join during office hour time slots, right? The other thing I want to point out is that we are working on finding some new times to hold office hours that will hopefully better accommodate some of you that are in different time zones, right? The staff, I also do want to point out though, everybody's under a lot of stress. That includes the staff. And so, we also need to think about the type of office hour load that we can support well. But we do want to make sure that we are accommodating people, particularly some of you that are on much earlier schedules, right? That may not be able to join us at office hours starting at noon. So we may shift that time a little bit to try to at least get a couple of hours where people from, Korea can come online and join us. All right, so announcements for today. The midterm is on Wednesday, so there's a few changes to the schedule this week designed to accommodate the midterm. There is no lab tomorrow, so we will run a meeting during lab time that you are welcome to join if you have questions about the midterm. The normal TAs and CAs and staff labs will be online during normal lab hours and there to help you. So if you have questions, please come by, particularly if they're conceptual questions. If you have questions about, the homework assignment or the NP, use the help system. Today's homework's not due till Wednesday. Again, this was designed to give you a little bit more time to prepare for the midterm. There's no coders on the midterm. Chapter 7 is due for next week's quiz, and we'll start taking up chapters one at a time again starting next week. I have virtual office hours online. I'll post a link to that later from 4 to 5 today, so please come by and say hi, or if you have questions or just want to hang out. Anyway, I'm going to go check the comment section for questions. I know we got started a little bit late, but I don't see too much here. I hope you guys are ready for the midterm. Good luck to the orange team that's finishing up MP3. So the blue team, this is it, right? You guys are almost done. MP4 is the last MP checkpoint, right? You have 2 weeks to finish it up, finish strong, get this thing done, and that's it, right? You guys are really close to the finish line on the MP, right? You should be able to smell success and sort of smell the good feeling that you're going to have, at least for a few minutes, if you're me, when you finish it and you really get the app to work completely, right? Because that's not too far down the road. All right, so as always, stay safe and well, guys. Take care of yourselves. Remember, a lot of you are in positions where you may need to take care of other people around you, but you have to take care of yourself first. If you don't take care of yourself, you're no good to anybody else. So, practice self-care, be good to yourselves, be patient with yourself. Start to realize this is a long-term thing. We're going to be in this together for a while. My wife and I were listening to a podcast the other day, Brene Brown, some of you may know, and she had this great metaphor about sort of this being the point where we need to settle the ball, right? If you're playing soccer, you get a high pass, it kind of is a little out of control. First thing you need to do, settle the ball, get it down to your feet, and then you can decide kind of how to move forward. So I think the first couple of weeks of this, it's been adrenaline, it's been stress, it's been a lot of new things. This is the point now where I think together as a class and as an academic community, it's time for us to kind of zero in, focus, and get the most out of the semester that we can given the circumstances. We're going to do everything we can to help, and I think you guys will be fine and do really well. Good luck. I will not see you on Wednesday. I will do a live streamed class on Wednesday at a different time. I'll post that on the forum. Participation is not counted for any of these live streams, including Wednesday. I just do it on live stream because it's more fun, but there's no obligation to join. You can watch it whenever you want. I wish you the best of luck preparing for the midterm. Please come join us again on tomorrow's lab office hours, today through the help system or the forum or office hours. I've got Zoom office hours. You guys are probably getting sick of Zoom, so am I. I will see you soon.